Your Kubernetes cluster is about to fail, and the standard monitoring tools won't tell you why until it is too late. Imagine scaling a large language model like Llama 3 across 100 nodes. Each pod demands 140 gigabytes of model weights to even begin execution. Suddenly, your VPC network bandwidth is completely saturated by parallel image pulls and weight transfers. The storage backend chokes, and nodes stop responding to heartbeats because the CPU is trapped in a permanent I/O wait state. Kubernetes, originally designed to orchestrate 50 megabyte microservices, begins firing OM kills and crash loop backoff errors as it tries to treat a massive LLM weight as a simple container layer. This is the weight catastrophe structural failure where the control plane loses its grip because the data plane is overwhelmed by the sheer physical gravity of AI models. This silent crash is occurring in production environments worldwide as teams attempt to shoehorn generative AI into infrastructure that was never built for this scale of state. By the end of this lecture, you will understand the deep architectural friction between cloud-native standards and the reality of generative AI. To survive the AI era as an infrastructure architect or a professional engineer, you must look beyond simple container orchestration. We are witnessing a fundamental impedance mismatch. Kubernetes assumes that workloads are ephemeral, stateless, and lightweight. In contrast, LLM inference is massive, tightly coupled to specific GPU hardware, and carries an enormous state in the form of KV caches and model weights. From the perspective of high-level systems design, this creates a resource gravity that traditional schedulers cannot calculate. We must evaluate these failures through the lens of performance guarantees and architectural mastery. We aren't just deploying software anymore. We are managing the complex interplay between memory bandwidth, GPU topology, and distributed weight loading strategies like P2P or specialized file systems. If you don't re-engineer your platform to account for this hardware coupling, your AI-ready cluster will remain a house of cards. But is the network really the only bottleneck? There are deeper, more fundamental assumptions within Kubernetes that AI workloads violate every single second, as we will explore in the next chapter. Kubernetes was originally architected for the cloud-native era, where applications were decomposed into lightweight, ephemeral microservices. In this legacy web model, pods are cattle disposable, fast to scale, and consuming minimal memory or CPU. However, a modern large language model container is the complete opposite. We are talking about heavy pets that require 40 GB to 80 GB of RAM just to load, staying active for long durations due to the massive cost of initialization. When you attempt to manage a 175B parameter model using standard horizontal pod autoscalar logic, the overhead of the start-stop cycle becomes a performance killer. The assumption of high-density bin packing for CPU tasks fails miserably when a single pod demands an entire H100 GPU or a multi-node cluster for tensor parallelism. This fundamental mismatch between lightweight ephemerality and heavyweight persistence is the first crack in the Kubernetes foundation. But if you think resource density is the only issue, wait until we look at the network pipe. In traditional CI/CD, pulling a 500 MB Docker image is a trivial task. In the AI era, we face data gravity on an unprecedented scale. Loading a Llama 370B model requires pulling nearly 140 GB of weights from a registry or a distributed file system like S3 or PVC. This creates a massive I/O weight state that Kubernetes is not natively optimized to handle. The standard container lifecycle doesn't account for the model load phase, which often takes longer than the actual container start. If 3 pods start simultaneously on the same node, they saturate the 10 GB piece network interface, leading to a cascading failure of liveness probes. We are seeing a registry bottleneck where the control plane assumes the pod is ready, but the GPU memory is still being populated. This data transfer latency breaks the responsiveness expected of an automated orchestrator. Does this mean we simply need faster networks? Not necessarily. The problem lies deeper within how Kubernetes decides where to put these workloads. The default Kubernetes scheduler is built for bin packing, ending any available slot for a pod based on CPU and memory requests. But AI workloads are GPU native and care about physical topology. If the scheduler places 2 pods on the same node but on GPUs that aren't connected via NVLink, performance drops by 40% due to PCI bottlenecks. We call this GPU fragmentation. Kubernetes often treats a GPU as a monolithic integer resource, for example, GP1, ignoring the nuances of HBM bandwidth, multi-instance GPU, MU slicing, or collective communication requirements like NCCL. When you scale to multi-node inference, the scheduler's lack of topology awareness causes pods to be scattered across the rack, introducing massive network hops for simple tensor synchronization. This leads to a scenario where your cluster says 60% utilized, yet your inference latency is twice what it should be. The paradox is that the more you optimize for utilization, the more you destroy performance. So how did we get here, and what was the original path of AI infrastructure? To understand the current crisis, we must look at where we started. AI infrastructure began in the world of legacy high-performance computing, HPC, dominated by Slurm and batch jobs. These systems were designed for long-running, static resource allocations. Then came the early MLOps era, where we tried to force these models into the Kubernetes microservices mold to gain the benefits of agility and APIs. But the modern LM-native era is different. It's not just about running a job. It's about real-time distributed inference serving that behaves like a database. We are moving from batch to interactive to distributed persistent workloads. The infrastructure is evolving from simple GPU pass-through to sophisticated virtualization and dynamic resource sharing. This evolution shows that Kubernetes is being stretched into a role it was never meant to play, a real-time, distributed supercomputer orchestrator. But what does a professional engineer think about this transition? From the perspective of an information management professional engineer, we are facing what I call the inference impedance mismatch. In database theory, impedance mismatch occurs when two different systems cannot exchange data efficiently because their structures are fundamentally different. Here, the structure of Kubernetes optimized for small, stateless, CPU-bound requests is incompatible with the structure of LLM inference large, stateful GPU-bound, and memory-intensive. As architects, we must realize that Kubernetes is no longer just a container runner, it is becoming a hardware-software co-design platform. We need to manage not just the code, but the information flow between HBM NVLink and the RDMA network. If we fail to solve this mismatch, we end up with the invisible cost of underutilized H100s, which can bankrupt an AI project faster than any security breach. Now, let's wrap up these foundational conflicts before we dive into the specific technological stack that solves them. In summary, Kubernetes is breaking because its core assumptions, lightweight pods, fast startup, and simple bin packing no longer hold true for AI workloads. We've identified the heavy pet problem, the registry bottleneck, and the failure of topology-unaware scheduling. We've also traced the evolution from batch HPC to the complex distributed inference needs of 2026. This chapter set the stage by showing you what is broken. But knowing what is broken is only half the battle. To fix it, we need a new taxonomy. We need to categorize these new infrastructure layers from the silicon level to the serving framework level in a way that allows us to build a truly AI-native stack. In the next chapter, Systematic Taxonomy of the AI-native stack, we will stop complaining and start building the blueprint for the modern AI data center. You don't want to miss how we categorize the LPU and RDMA layers into this new world order. To architect a robust 2026 ready AI infrastructure, we must first establish a systematic taxonomy. The landscape has evolved beyond simple containerized wrappers. We now face a divergence between container-native and virtualization-native approaches. On one side, we have VLLM and Hugging Face TGI pushing the limits of pod-based serving through sophisticated packet attention mechanisms. On the other, the rise of llm-d LLM daemon paradigm utilizes Kubernetes to wrap inference engines in lightweight virtual machines for enhanced security and resource isolation. In high-scale production, engineers are moving toward a hybrid model where the orchestration layer must treat the GPU not just as a peripheral, but as the primary compute citizen. Understanding this taxonomy is the first step in moving from a reactive infrastructure to a proactive AI platform that can scale to trillions of parameters without collapsing under its own management overhead. This structural shift is fundamental because it changes how we view the lifecycle of a deployment. But wait, is just choosing a runtime enough to handle the sheer volume of LM requests? A sophisticated AI-native stack is no longer just a two-layered model of hardware and software. By 2026, we have identified a critical three-plane architectural model: the control plane, the data plane, and the newly defined inference plane. The control plane remains the realm of Kubernetes API servers and schedulers, managing the where and when. The data plane handles the massive throughput of high-speed RDMA and InfiniBand networking. However, the inference plane is where the true complexity resides. This layer is responsible for weight distribution, KV cache management, and dynamic batching. In a distributed LLM scenario, the inference plane must orchestrate the prefill and decode phases across different hardware units to maximize TFLOPS utilization. For a professional engineer, missing the distinction between these planes leads to noisy neighbor problems where model loading saturates the storage network, killing real-time inference latency. The synergy between these three layers determines whether your cluster can sustain a 99% SLI for LLM token generation. What happens when the isolation provided by standard Kubernetes pods isn't enough for sensitive multi-tenant workloads? When designing for multi-tenancy, we must weigh the trade-offs between pod-based and KubeVirt-based inference. Standard Kubernetes pods offer the lowest overhead and fastest cold start times, making them ideal for bursting serverless-style inference. However, they share the host kernel, which poses a significant security risk when running untrusted model weights or third-party adapters. KubeVirt-based inference, often referred to as the llm-d pattern in advanced frameworks, provides hardware-level virtualization. While this adds a slight overhead to memory and CPU, it offers superior isolation and allows for custom kernels optimized for specific GPU drivers. In a zero-trust AI environment, KubeVirt is becoming the standard for 2026 deployments. We see this choice directly impacting the blast radius during a driver crash or a memory leak in the inference engine. Choosing between them is not about which is better, but which fits your security vs latency profile. This choice leads us to a more pressing question: how do we even schedule these massive units of compute effectively? This is where standard Kubernetes scheduling breaks down completely. Standard Kubernetes scheduling is greedy and individualistic. It schedules one pod at a time. For distributed LLM inference using model parallelism, this is a recipe for disaster. Imagine a 4 GPU model where the scheduler places 3 pods but fails to find a slot for the 4th. The first 3 pods sit idle, consuming expensive H100 resources while waiting for a resource that might never come. This deadlock is solved through gang scheduling or scheduling. By using frameworks like Volcano or the Kubernetes scheduler plugins, we implement an all-or-nothing logic. The job only proceeds if all required GPU resources are available simultaneously. This prevents resource fragmentation and ensures that high-priority inference jobs don't get stuck in a partial start state. In the context of 2026 AI platforms, gang scheduling is no longer optional. It is the prerequisite for financial efficiency in GPU clusters. But wait, even if all pods start together, what if they are placed on opposite sides of the data center? The latency would kill the performance. To truly unlock GPU performance, the scheduler must be topology aware. Modern AI servers utilize NVLink for ultra-fast GPU to GPU communication, which is orders of magnitude faster than standard PCI or network hops. If your scheduler places 2 pods on the same node but on different PCI switches without an NVLink bridge, your internode communication becomes a massive bottleneck. A topology-aware scheduler reads the hardware hierarchy knowing exactly which GPUs are connected via NVLink, which share a PCI root complex, and which are on separate llm-d nodes. By prioritizing bin packing based on communication affinity, we can reduce inference latency by up to 40%. For the platform architect, this means implementing the topology manager and ensuring the node feature discovery (NFD) is correctly labeling hardware traits. It's the difference between an LLM that feels like a human conversation and one that stutters, but is scheduling just about the start. What happens when a higher priority job arrives? Synthesizing these principles, a stable AI-native Kubernetes platform requires a fundamental shift in scheduling strategy. We must combine gang scheduling for availability, topology awareness for performance, and preemption logic for cost efficiency. In this 2026 paradigm, the scheduler is no longer just a resource matcher. It is a performance orchestrator. It must understand the relationship between the model size, the weight sharding strategy, and the physical location of the data. We have covered the structural taxonomy and the mechanics of scheduling, but this is only the foundation. The real magic happens inside the inference engine itself, where we optimize the memory of the LLM. In the next chapter, we will dive deep into the llm-d pattern and the breakthrough principles of KV-cache optimization that allow us to serve thousands of users on a single cluster. Prepare your technical mindset for Chapter 4, Deep Principles of llm-d and KV-cache Optimization. In the traditional Kubernetes world, a pod is a black box. The scheduler sees CPU, memory, and perhaps a GPU count, but it remains blissfully unaware of the model weights or the KV cache residing within. This is where the llm-d or LM distributed layer becomes critical. It acts as the intelligent bridge between the container orchestrator and the high-performance inference engines like VLLM, TensorRT-LLM, or DeepSpeed MAI. From a professional engineer's perspective, this is a shift from infrastructure-agnostic scheduling to model-aware orchestration. Without this layer, your cluster is essentially blind to the actual compute patterns of a 70B or 175B parameter model. By implementing an llm-d framework, we can manage the lifecycle of distributed model weights across multiple nodes as a single logical unit. This is not just about running a container. It's about managing a stateful, high-throughput distributed system that must scale in subseconds. But why does a single model need such a complex distributed management layer in the first place? The answer lies in the fundamental physics of LLM execution, specifically the mismatch between the prompt and the generation phases. To maximize throughput, modern LLM infrastructure must embrace the prefill and decode split. During the prefill phase, the model processes the entire input prompt simultaneously, which is highly compute-intensive and benefits from massive parallelization across GPU cores. In contrast, the decode phase generates tokens one by one, making it memory bandwidth bound and highly sensitive to latency. If we combine these phases in a single GPU, the heavy prefill tasks often block the quick generation of tokens, leading to high jitter and poor user experience. By decoupling these into separate prefill nodes and decode nodes, we can optimize each hardware set for its specific workload. Prefill nodes utilize high-throughput compute units, while decode nodes are optimized for fast KV-cache access and low-latency networking. In the field, we see this separation increasing throughput by up to 2-3 times compared to monolithic setups. This is the separation of concerns principle applied to AI-native compute. However, this split introduces a new challenge. How do we transfer the massive intermediate states from the prefill stage to the generation stage without killing our network? Next, we examine the underlying plumbing that makes this fast transfer possible. In a distributed llm-d environment, standard Kubernetes networking is simply too slow. We are dealing with gigabytes of KV cache data that must move between GPUs in milliseconds. This necessitates the use of RDMA or remote direct memory access, specifically through protocols like ROSEV2. By bypassing the CPU and the kernel's TCP/IP stack, RDMA allows one GPU to write directly into the memory of another GPU across the network. Furthermore, llm-d must manage worker discovery. When a new GPU worker joins the cluster, the system must automatically register it into the NCCL, NVIDIA Collective Communications Library, click and rebalance the model shards. This is dynamic infrastructure at its peak. We aren't just talking about a static configuration, we are talking about a living, breathing mesh of high-speed interconnects. If your Kubernetes CNI cannot handle the specific headers of ROCE or lacks the performance of a dedicated SRI-OV interface, your expensive 800s will sit idle, waiting for data. But how do we actually represent this complex networking and pod configuration in a way that an ops team can manage? It's time to look at the actual Kubernetes manifests that define these AI-native jobs. To manage this complexity, we use a custom resource definition, or CRD, often named something like llm-d or Inference service. This YAML doesn't just define a container image. It defines the number of model shards, the tensor parallelism degree, and the pipeline parallelism stages. Notice the worker spec. In this example, it explicitly requests GPU resources and configures the environment for the distributed engine to initialize its communication mesh. In practice, this allows us to scale out a Llama 3 70B model across 4 or 8 GPUs with a single kubectl apply command. This is the automation that transforms fragile AI experiments into resilient AI platforms. We also include affinity rules to ensure that pods belonging to the same model shard are placed on the same physical node or rack to take advantage of NVLink. This level of declarative configuration is what separates a legacy cluster from an AI-ready one. But even with perfect scheduling, we face a silent killer of performance, the KV cache. Even if your compute is fast, if your memory management is inefficient, your tokens will crawl. Let's dive into the art of KV cache sharing. What is the KV cache? Simply put, during an LLM conversation, the model needs to remember every previous token to generate the next one. These mathematical representations, keys, and values are stored in GPU VRAM. As the conversation length increases, the memory required for the KV cache grows linearly. For a long context model like GPT-4 or Gemini, this cache can easily consume tens of gigabytes. In a multi-user environment, if every single request starts its own cache from scratch, the GPU memory will be exhausted almost instantly, leading to out-of-memory errors even when the model weights themselves fit. This is the single biggest bottleneck in multi-turn LLM conversations. We are effectively playing a high-stakes game of Tetris with GPU memory blocks. To solve this, we must move away from static memory allocation toward dynamic, paged memory management, similar to how operating systems handle virtual memory. But what if we could share this memory across different users or even different nodes? This is where distributed caching enters the picture. In a sophisticated AI-native stack, we distinguish between local caching and distributed KV caching. Local caching, often implemented via paged attention in VLLM, manages memory blocks in a single node to prevent fragmentation. However, in a large-scale cluster, users might have their requests routed to different nodes. If node A has the KV cache for the first half of a long PDF analysis, but the next question is routed to node B has to recalculate everything. This is a massive waste of energy and time. A distributed KV cache or a global registry, like Radix Attention, allows different nodes to share and look up common prefixes. If multiple users are asking questions about the same documentation or using the same long system prompt, the system can reuse the cached states across the entire cluster. We are essentially moving toward a content-addressable memory system for LLMs. This architecture requires a global metadata store that tracks which node holds which part of the attention graph. But does this complexity actually translate into measurable performance gains for the business? Let's look at the hard numbers. When we implement advanced cache sharing, the performance metrics shift dramatically. We track two primary KPIs, time to first token, TTFT, and time per output token, TPOT. TTFT is the most critical for perceived user experience. It's the delay between hitting enter and seeing the first word. With a global cache hit on a long prompt, we can reduce TTFT from several seconds down to milliseconds because we skip the entire prefill calculation. In our benchmarks, prefix caching can increase the overall throughput, tokens per second, by over 50% for typical RAG-based applications where the context remains largely the same. Look at the table here. When a cache hit occurs, the latency drop is nonlinear. It's a paradigm shift. However, as an architect, you must balance this with cache eviction policies. Just like a standard web cache, you cannot store everything forever. You need LRU, least recently used, or frequency-based eviction that is aware of GPU memory pressure. This brings us to a crucial question. How do we route users to the specific node that already has their cache? The answer is not a standard load balancer. We need something more intelligent. We have covered a lot of ground in this chapter. We started with the llm-d layer that provides the distributed intelligence Kubernetes lacks natively. We saw how separating the prefill and decode phases allows us to optimize for both throughput and latency. Finally, we looked into the KV cache, the silent memory consumer, and how distributed prefix sharing can reclaim massive amounts of VRAM and drastically lower TTFT. These are the deep principles that separate a standard cloud engineer from an AI infrastructure architect. But remember, an optimized engine is useless if the traffic cannot find it. In a world where every pod has a different version of the cache, a standard round-robin load balancer is your worst enemy. It will constantly send users to cold nodes, destroying your cache hit rate. To solve this, we need the next level of the stack. In the next chapter, we will explore intelligent routing using the Kubernetes Gateway API to ensure your traffic is always cache-aware. Traditional Kubernetes ingress was designed for simple microservices, but it fails to meet the sophisticated demands of LLM and inference in 2026. As an infrastructure architect, you must realize that standard L7 load balancing is no longer sufficient when dealing with multi-gigabyte model weights and heterogeneous GPU clusters. Enter the Gateway API, the evolved successor to Ingress. Unlike the monolithic Ingress resource, Gateway API provides a role-oriented, extensible framework that separates infrastructure concerns from service routing. This is critical for AI platforms where the infrastructure team manages the physical GPU compute resources, while the MLOps team manages model-specific routing logic. By using the Gateway API, we gain the ability to handle protocol-specific complexities and advanced traffic splitting that were previously buried in vendor-specific annotations. This shift allows for a more robust control plane that can handle the massive throughput and low latency requirements of modern generative AI applications. But standard routing is just the tip of the iceberg. What happens when we need to route based on the context of the prompt itself? In the world of LLM serving, not all requests are created equal. A short classification prompt requires significantly less KV, cache, memory, and compute time than a long-form document summarization request. To optimize cluster efficiency, we must implement content-aware routing. By leveraging Gateway API with specialized controllers, we can inspect headers or request metadata to perform token-based routing. For instance, requests with high expected token counts can be routed to GPU nodes with higher VRAM or specific llm-d configurations optimized for long context windows. Similarly, we can implement model-based routing, where pro models are directed to high-performance H100 clusters, while light models go to cost-effective L40 nodes. This granularity prevents the noisy neighbor effect where long-running inference tasks starve short, latency-sensitive requests. We are essentially moving from a simple round-robin approach to a multi-tier, priority-aware distribution system. This sounds complex to implement manually, but wait until you see how simple the configuration becomes with a unified gateway spec. Let's look at the actual implementation. In this code example, we see an HTTP route resource managing a canary deployment for a new version of an LLM. Notice the simplicity. We define two backends, llm-v1 stable and llm-v2 RC, and assign weights to them. By using Gateway API's native support for weighted traffic, we can safely roll out a 175B parameter model by gradually shifting 10% of the traffic and monitoring for regressions in perplexity or latency. Furthermore, we can use matches to route specific users or internal testers to the new model based on ANC's use canary header. This YAML structure is the standard for 2026 AI infrastructure, providing a declarative way to manage complex model lifecycles without touching the core application code. This abstraction layer is what allows our infrastructure to remain resilient while the models themselves change weekly. Routing is solved, but the biggest bottleneck in AI infrastructure remains: the unpredictable nature of GPU demand and the dreaded cold start. One of the most common mistakes I see in the field is using the standard horizontal pod autoscaler, or HPA, based on CPU or memory for LLM workloads. In an inference cluster, CPU usage is often misleading. Your CPU might be idle while the GPU is at 100% utilization, or conversely, memory might be full just because of model weights, not active traffic. For 2026 AI platforms, we must transition to key-day Kubernetes event-driven autoscaling. Key-day allows us to scale based on custom metrics that actually matter: active request count per GPU, queue length in the inference engine, or even time to first token, TTFT. If the request queue for a specific model exceeds a threshold, key-day can trigger the provision of new GPU nodes immediately. By scaling based on the inference concurrency metric rather than generic system metrics, we ensure that we aren't wasting expensive GPU resources during lulls, nor are we throttling users during spikes. Even if we scale perfectly, loading a 70B parameter model takes minutes. How do we make those minutes disappear? The cold start is the nemesis of AI infrastructure. Loading a large model from a remote registry can take several minutes, leading to unacceptable user latency. To mitigate this in a technical sense, we employ 5 critical techniques. First, speculative loading, where we predict traffic increases and start pods before they are needed. Second, container streaming, using tools like Stargs to start the pod without waiting for the full image download. Third, P2P model distribution within the cluster to bypass registry bottlenecks. Fourth, pre-warming KV caches for common system prompts. And finally, using local NVMe caching for model weights on GPU nodes. By implementing this checklist, we can reduce the time to ready from 300 seconds down to under 20 seconds. This is the difference between a seamless AI experience and a broken one. We've covered the components from the scheduler to the gateway. Now let's see how they all lock together in one final, cohesive 2026 architecture. We have now traversed the entire stack of modern inference serving, from the scheduling challenges of giant weights to the deep optimizations of llm-d and the KV cache, and finally to the intelligent routing of the gateway API. This architecture is not just a collection of tools. It is a holistic system designed to overcome the fundamental mismatch between static Kubernetes design and dynamic AI workloads. In this summary, we see how the control plane handles the where scheduling, the data plane handles the how llm-d, and networking plane handles the who gateway API. This setup is powerful, but how do we turn these technical components into a strategic business advantage? That's the subject of our final chapter, the 2026 AI Infrastructure Blueprint, where we will synthesize everything into a production-ready roadmap for the next era of computing. To conclude our architectural journey, let's look at the production-ready blueprint for 2026. Building an AI infrastructure on Kubernetes requires a fundamental shift from general-purpose orchestration to specialized AI-native management. From the perspective of an information management professional engineer, we must categorize our requirements into three pillars: resource efficiency, latency determinism, and architectural resilience. This 10-point checklist represents the critical technical standards observed in high-scale industry environments. You must verify if your cluster supports dynamic resource allocation (DRA) to move beyond simple integer GPU requests. Are you utilizing topology-aware scheduling to minimize NVLink latency? Your KV cache management decoupled from the pod lifecycle to allow for seamless preemption. Industry frameworks like ISO IEC 4-2001 emphasize that AI governance starts with infrastructure reliability. If your platform cannot handle the non-deterministic nature of LLM workloads today, it will certainly fail under the demands of tomorrow's agentic workflows. Use this checklist as your foundational audit tool for the 2026 era. But wait, even with these optimizations, the very nature of how we run containers is about to change. Let's look at the final horizon. Looking toward the 2026 horizon, the boundaries between the application and the infrastructure are blurring significantly. The overhead of traditional container runtimes is becoming a primary bottleneck for ultra-low latency inference, leading to the rise of shift-down technologies. WebAssembly or WASM is emerging as a critical alternative for AI functions, offering near-native execution speed and cold start times measured in milliseconds, a massive leap over Docker. Simultaneously, eBPF is transforming from a simple networking tool into the central nervous system for AI observability, allowing us to monitor GPU kernel, execution, and memory throughput without any application-level instrumentation. In the field, we are seeing a transition from running models to orchestrating intelligence where the infrastructure itself understands the semantic state of the LLM. By integrating these innovations, you move beyond the limitations of legacy Kubernetes. This concludes our deep dive into why LLMs break Kubernetes and how we must rebuild it. The future of AI is not just about larger models, but about the invisible, intelligent infrastructure that sustains them. Thank you for joining this masterclass on the next generation of AI platforms.